Hi and welcome to Vulkan from Zero to Hero.
In this section, we are going to draw our first triangle.
In this video, we are going to create image views. Welcome back. In the previous video, we successfully created swap chain. Now we need to create image buffer for swap chains. First, we need to get the count of available images for this swap chain. So call vk get swap chain images khr. This function needs the following parameters. The first parameter is Vulkan device, same as most of other Vulkan functions. Second one is swap chain object. And third, send swap chain image view object by reference. And finally, send null pointer because we just want to get the number of swap chain images. After executing this function, we should have the number of swap chain images. It is safe to check the return result of this function and print any necessary message to the output in case of any unexpected problem. Now create vector of vk image with maximum size of swap chain image count. Then call vk get swap chain image khr again and pass the vector to the function in order to get swap chain images data. Same as before, make sure to check the return result of this function. Now we have a vector which contains vk image objects. It's time to create image view for each object. So let's iterate over all swap chain images and create vk image view create info for each of them. First, set the type of this structure. I mean, image view create info. Then pass null pointer to pnext, 0 for flag. The swap chain image as vk image. We want to create 2D image. Also, make sure to set the format of this image view based on the format of desired swap chains format. Set vk component swizzle R, G, and B to related members of image view components. Set vk image aspect color bit to subresource range.aspect mask. And finally, the base bitmap is 0. The base array layer is 0. Both level and layer counts are 1. After you initialize VK image view create info, now it's time to create an image view. We've already defined a structure called image_view, which contains a member type of VK image. So let's assign our swap chain image to it and call VK create image view function in order to create our image view. This function needs the following parameters. Same as others, the first parameter should vk_device. The next one is a pointer to color image view create info. We don't need any callback, so let's just set null pointer, and the final parameter is a pointer to image view, which will be created after executing this function. Make sure to create a boolean variable and let's name it _error in order to handle any unexpected errors. We will use this variable in order to break from loop and print out any necessary message to the output. We need to store width and height information of this image view. Also, we need to create an image view attachment description. Also, we need to create an image view attachment description. So make sure to set the desired format of this image view. In this case, we are going to use BGRA uniform with 32 bits. Set VK sample count 1 bit for sample. We should set load operation flag, which we use load operation clear. And set a store operation store as the store operation flag. For stencil load operation, we use load operation don't care. And for stencil store operation, set store operation don't care. The initial layout should be VK image layout undefined. And the final layout should be VK image layout present source KHR. Now the final step is to initialize attachment, reference, and finally store this image view in present view. It's time to create depth buffer. In computer graphics, depth buffering, also known as z-buffering, is the management of image depth coordinates in 3D graphics. First, we need image create info for our depth buffer. We need a function like this in order to get supported format by this GPU. For instance, we need to find whether this device supports 32 bits depth format or 24 bits depth format with features such as tiling, optimal, and format feature depth stencil attachment. Let's declare this function in device manager header and then implement it in device manager.c++. All we need to do is to look up our desired formats from physical device formats. Now get back to the depth buffer and check the situation that the target machine won't support our desired depth format. Then it's better to print a message to the output and return false. Now let's set values for members of depth stencil image create info. Set null pointer for pnex. We need image type 2D. Make sure to set the desired depth format, width and height of depth buffer. Set 1 to depth, MIP maps and array layers. Set VK sample count 1 bit for samples. VK image layout undefined to initial layout. Set usage of depth buffer. And finally, sharing mode, which must be exclusive. Then create a memory allocate info, and now we can create depth image via VK create image. Check the return result of this function in order to print any necessary message to the output in case of unexpected error. After we've created image, we should get memory requirements for this depth image buffer. Call vk get image memory requirements. We need another function in order to get memory type based on the required memory properties. Let's define this function as static And in device manager.cpp, let's implement it like here. Iterate over all memory properties and get the index of type. Now we can allocate memory for depth image and finally bind to depth image memory. Okay, we need depth as stencil image view, so create an image view create info and initialize it like this. After that, just call vk create image view in order to create image view. Finally, make sure to set up depth image view descriptions. Okay, let's build our project and then let's debug our code. So you can see everything works fine. So we can move to the next step, which is creating semaphores. In the next video, we are going to create semaphore.